Hello, and welcome to the seventh and last probability video. We've saved the best one till last, tree diagrams. And these help us work out probabilities of combinations of events. We can work out all kinds of and or events using these. So let's have a look at an example. We start off with a very simple example. We've got a fair and biased coin, we toss it twice, draw a tree diagram to calculate the probability of getting at least one head. So at least one head, this is the secret really, is to consider all the options before you sort of get into the question. At least one head means one head or two heads. Okay, now we need to know the following before we start. The probability of getting a head is half, probability of tail, getting the half. So let's have a look. So we're going to draw the kind of framework first. We've got our first toss. Now that could be a head or it could be a tail. Now if we get a head on the first toss, on the second toss we could get a head or we could get a tail. And similarly, if we get a tail first time, we could have a head or a tail. Now let's put some numbers in them. On the first toss, we've got probability of a head and probability of tail, both are half. Now, on any connected set of branches, the total probabilities must equal 1. So in other words, if we add up half and a half, we get 2 halves, which is 1. And it seems obvious here, but sometimes we'll be given the probability of one branch and we have to work out the probability on the other branch, but we use that fact that they add up to give 1. Now on the second toss then, we've got half and a half, and once again they add up to 1, and we've got a half and a half, and they add up to 1. So now we can start working out some of the probabilities. So let's have a look at this first path here. So if we go along there and along there, that will give us the probability of getting a head and a head. Now what's that? Remember doing that one on a couple of videos ago? And is times. So we've got a half times a half. Now a half times a half is a quarter. Okay, let's have a look at our next route. Now that goes along there and then down there. Now that tells us the probability of getting a head and a tail. So that's a half multiplied, because it's and, a half. Now half times a half is a quarter. Let's have a look at the next route, and that goes along tail and head. So that tells us the probability of getting a tail and a head, and you can guess it is a half times a half, which is a quarter. And then the last one, it's tail followed by tail. So it's tail and a tail, and once again it's a half times a half, which I'm sure you know by now is a quarter. You probably knew that anyway. Now all those probabilities over on the right hand side, they should add up to give us 1. And if we have a look, we've got 4 quarters, and that is 1. So it's good. And that's, oh there we go, a bit flashy. And that's quite a nice little check that we haven't made any horrendous mistake if you add up those probabilities there. So now we can use all that information to find out all kinds of things. We could use it to calculate the probabilities of a head and a head, or a tail and a head, or we could also calculate sort of more complex things like the probability of 2 the same, or at least one head, or something like that. So let's see how we do that. We're going to calculate the probability of at least one head. Now that means that at least one head is 2 heads, or a head first and a tail, or a tail first and a head. Okay, so we've got the probability of head and a head. Then you see a plus. Now that plus is there because that equates to the word or. Head and a tail, or, which is plus, tail and a head. So the probability of at least one head is the probability of 2 heads, or head and a tail, or tail and a head. So let's get that one from there. That's a quarter. In fact, they're all a quarter, aren't they? So that's a bit silly, really. That bit. Quarter and a quarter and a quarter is 3 quarters, and that's the probability of getting at least one head. Let's have a look then. Let's do something a bit more complicated. We've got a fair unbiased dice. It's rolled twice. Draw a tree diagram to help you calculate the probability of getting at least 1 5 on the 2 rolls. Okay, so we're looking here not at all the numbers we could get on a dice, not all of 1, 2, 3, 4, 5 or 6. We're interested in 5, or anything else is just not 5. So we need to know the probability of getting a 5 is 1/6, and not getting a 5 is 5/6. So let's have a look. The first dice roll, that could be a 5 or not 5. And the second dice roll, well, if we get 5, the second dice roll could be a 5 or not 5. And it could be a 5 or not 5 there. Whoop, some numbers have appeared. Let's have a look then. Yes, so the probability of getting a 5 is 1/6. Not 5, it's 5/6. What are we going to do with those to make sure we've got it right? Or make sure that we haven't made a terrible mistake, I should say, is add those up. We get 6/6, which is 1. That's nice. And in fact, the probabilities are just then repeated on the other sets of branches. So those two add up to get 1, and those two add up to get 1. So that's good. So now let's work out going along these routes. So let's get this first path, which is that one there. And that's the probability of getting a 5 and a 5. So that's 1/6. And is times 1/6. 1/6 times 1/6 is 1/36. Next path we're going to look at is that one there. Okay, so that's the probability of a 5 and a not 5. Okay, so that's 1/6. Remember that 5 with a bar on top means not 5. That's 1/6 times 5/6, which is 5/36. Next one is not 5 and a 5. Okay, so that is 5/6 times 1/6, which is again 5/36. The last route we're going to take is down there, so that's not 5 and not 5, and that is 5/6 times 5/6, which is 25/36. Now I'm just going to check all that stuff on the right hand side adds up to 1, and we've got all 36ths. 1 and 5 is 11 plus 25. Yes, 36 1 whole. So the probability of at least 1 5 is the probability of getting in 2 5s, or 5 and not 5, or not 5 and 5. So we've got 1/36, 5/36, and 5/36. So it's 11/36. The probability of getting at least 1 5 is 11/36. We could have done it the other way. We could say, okay, what have we got that doesn't satisfy at least 1 5? So the only thing not satisfying at least 1 5 is no 5s. So we take that away from 1. 1 minus not 5 and not 5. So it's 1 minus 25/36, which fortunately gives us the same. So there we go. Now what we've done so far, tree diagrams where the probabilities are repeated from set of branch to set of branch. Now let's have a look. We shall now draw a tree diagram where the probabilities change from branch to branch. Let's look at the question to see why. Okay, so there's Iorwerth with his 15 shirts, 4 are plain, 11 striped. He selects 2 shirts to take away. Draw a tree diagram to help you calculate the probability of him selecting no more than 1 plain shirt. So no more than 1 plain shirt, what does that mean? That means he can take 1 plain shirt, or he could take no plain shirts, but he can't take 2 plain shirts. We want the probability of him having no more than 1. So it's 1 or less. 1 or fewer, I should say, shouldn't I? Now for the first shirt, the probability of picking a plain one, or P-plain, is 4 out of 15, or 4/15, while the probability of not plain, or striped, is 11/15. Okay, that's nice and obvious, but this is where it gets a little bit more complicated. When he comes to select the second shirt, we need to consider what he chose as his first shirt. Now if the first shirt is plain, he's now got 3 plains and 11 striped, total of 14 shirts. So that means the probability of picking a plain one is 3 out of 14, or 3/14, while the probability of not plain is 11/14. But what if the first shirt he picks is striped? So now there's 4 plains and 10 striped. So it's still 14 shirts, but different makeup, and 4 plains, 10 striped. So the probability of picking a plain one is 4/14, while the probability of not plain one is 10/14. So let's see how that affects the tree diagram. So we got a first shirt. Okay, it could be plain or not plain, and the second one. If he's got a plain first, it could be plain or not plain, and similarly there. So the framework is the same, but the numbers are going to be different. So for his first one, 4/15 probability of picking a plain, 11 for not plain. Let's just say they add up to 1. Yeah, they do. Now for the second shirt, if he chose a plain first, So because that is 4/15, this is now 3/14, and that's 11/14. But what if you picked a stripy one? Then the probability of picking a plain one is 4/14, and a stripy one, or not plain, is 10/14. So now we've got different numbers on different branches. Okay, so let's work out some probabilities. So our first root is there, P and P, plain and plain. So it's 4/15 times 3/14. That's 12 and a 210. Next path is P and not P. Okay, so that's 4/15 times 11/14. So that's 44 210ths. Next, not P and P. So that's 11/15 times 4/14, 44 210ths. And finally, not P and not P. So that is 11/15 times 10/14. Whoops, 11/15 times 10/14. So that's 110 210ths. Just make sure it all adds up to 1. We got all 210ths. We've got 12 and 44 and 44, so that's 100 plus 110. Yes, 210 210ths. Good. Now let's have a look then. We want the probability of no more than one plane. So which ones satisfy that? Well, plain and not plain, that's got no more than one plane. Or it could be not plain and plain. Or it could be two not planes. We haven't in any of those got more than one plane. Good, so that's 44 210ths, followed by 44 210ths plus 110. Okay, so that is 198 210ths. We can cancel that down to 99 105ths. There we go. We could have done it the clever way. We could say, okay, no more than one plane. So which ones satisfy, don't satisfy that, I should say. So that's the one where there's more than one plane, which is two planes. So it's 1 minus 12 210ths, which is, once again, 198 210ths, 99 105ths. So there we go, that's tree diagrams. We got the easy ones, the complicated ones. You're all ready for an exercise, which is just as well, because that's what's coming up next. And that's the end of the videos, so it's bye from me, and hope you're feeling like a probability expert now. Bye bye.